Check 1, 2.
Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody, and welcome. Welcome to another episode of Ask Us Anything About Electrochemistry. I am your solo host today. I'm Dr. Neil Spinner. I'm an electrochemical engineer with Pine Research, a company based in the United States. And my normal colleague sidekick, Alex Peroff, is not with me today, so I will be doing this by myself, so bear with me. Normally, Alex does a lot of this stuff, so I will do my best in his absence. Just a few notes at the beginning here before we get going, answering your questions about electrochemistry. As the name implies, this is a forum for you to type your questions in the chat. If you're watching on Twitter or on YouTube, you can type your questions anytime, and I will get to them and try to answer them as best I can. Just a few notes again. So this is, I think this will be episode 49 or so. So we've been doing this for quite a while, and this is an opportunity for us here at Pine to address some questions. We get a lot of questions through webinars, through our YouTube videos, through phone calls and emails with people doing their electrochemistry research. And very often we find that it's hard to answer those questions, in various ways without having the tools to draw a diagram, to draw an electrode surface, to have some of those kinds of interactive tools. And so this is a medium where I can do some of those things. And so that's why we've been doing this live stream. So we do encourage anybody to bring your questions to us. To that end, there are a couple pieces of advice that we like to give. So we want to encourage you to ask questions about anything. We will do our best to answer them, or I will do my best today anyway. There's a couple of extremes that we want to try to avoid. So for instance, if you just ask a question like, what is electrochemistry, or something very, very general, it perhaps is not the easiest thing to answer. It'll be a little too broad, right? But on the other hand, if you ask a question that's very, very specific, like what is the exact heterogeneous rate constant of the third electron transfer of the iron 2+ complex. I'm simply not going to know the answer to that unless I happened to do it during my PhD studies, which is probably pretty unlikely. So something in between either extreme of very, very general or very, very specific. And I will certainly do my best to answer that for you. Apologies in advance if anybody's names are mispronounced. I am mainly going on the information I have in front of me, which is usually your YouTube or Twitter username, which is not necessarily your name, but in any case, I will certainly do my best to answer. And if you are watching this after the fact, so this is not a live stream for you that you are watching the recording, you can type a question in the comments section and we will get to them there, or to queue it up for a future live stream to answer there as well. So there have been already a couple of questions. One was asked on a comment, as I just sort of said, to prove this point, I suppose. So I'm going to get to these questions first. If you have any questions and you're watching live, go ahead and type them in anytime. I'll get to them as soon as I can. But a user with the name devxpentatom 7932 asked a question. A question came to my mind: is how would a circuit diagram, how would it be if there was a Warburg impedance for an electrode with multiple coatings? Would the W, the Warburg infinite element, be present only in one part of the circuit? And then a follow-up comment with that in mind was, if in a substrate film 1, film 2 electrolyte multi-layer coating scenario, so this is like a substrate film situation with multiple films, the EIS circuit is given as, and he basically says R1 plus a Randles plus a Randles. Would the Warburg element be included so that it's basically R1 plus Randles with a Warburg plus the second Randles, or as R1 plus Randles with a Warburg plus Randles with a second Warburg, multi-layered. So basically asking about multi-layer diffusion. So I will try to get to this and answer this for you. And give me a moment to pull up. I have a few tools here I'm going to try to show you. So first of all, one of the things that you're asking about, of course, is related to substrate and film. Okay, so let me try to share this with you. I have to check if I need to share my, give me a moment. I'm going to share the presentation for you so I can kind of show you what I mean. Okay, so so to talk about this kind of an interface, and to answer your question, right, we're talking about a substrate and a film interaction. And one of the things that is done with that is to use a Randles element as the simplest representation of any electrochemical interface. So that would mean substrate film, film, or film electrolyte, anywhere where there's an interface between two dissimilar phases or species, you would basically imply a Randles element at this as the simplest kind of scenario. Okay, and so the simplest situation would be a substrate and a film, and then an electrolyte. Now these slides may not be perfectly applicable to what your question was, but it's also a relevant kind of a subtopic, which is to say, if I have a substrate and a film, does the film fully cover the substrate or does it not? Okay, that can adjust the model that you use. However, without getting too far down that pathway, just focus on the left side here, which is to say substrate and film, and the kind of model that you would apply to that would be something like this, where you you would have a leading resistor, which is the uncompensated ohmic resistance, a Randles element for the substrate-film interface, and then a Randles element for the film and the electrolyte interface. Now, again, this model sort of has a separate possibility. You could have a substrate electrolyte interface if the film doesn't fully cover the surface. That aside, to your question, if you have diffusion, where does the Warburg go? And what if would you put Warburg in both of these? So, and the third thing being that you have double film kind of a situation. Okay, so it's actually fortuitous that you've asked this question, because these slides are part of a webinar that I have given previously, maybe 2 years ago or so, where somebody submitted data to me with just such a similar situation. Basically, there were 4 layers instead of 3. So the first thing is that your proposed circuit model, which was like R1 plus a Randles, is missing a Randles element. If you have 4 layers, you will have 3 Randles elements, right? If this, again, this specific example in these slides, someone had steel, this HDG layer, a polymer layer, and then electrolyte. So don't worry about the specifics. But if you have this bottom layer as your substrate, and then this next layer is film 1, and then film 2, and then electrolyte, then you have a situation where you actually might have 3 Randles elements. Possibly. You may not. It depends. Some of these film substrate film interactions may be negligible, but in theory you would have actually 3. And for each interface present, you can propose that there might be one of those. Okay. Now, to that point, your sort of proposition here, and let me come back to my slide on where I'm not in a mode of presenting here. I want to just illustrate what I mean. So your proposition is effectively, okay, what if I want to add a Warburg element? And so basically something like, should it be here? Should it be here? Or should it be here? Right? I can have W, I guess these are 2, just to keep the numbers the same. You could have a W3, or could you have a W4? So the question is kind of in general, as I understand it. Let me zoom in to show you here. Basically, which of these should have a Warburg, or is it all of them, right? And apologies that it's a little bit crude drawing here. I'm trying to. So does the Warburg go here? Does it go here? Does it go here? Or does it go in all 3, right? Now, the short answer is that probably it doesn't go in these ones, because the Warburg, especially the way you've proposed your question, is an infinite, semi-infinite plane Warburg. And each of these films has, at least most likely, a finite length to it, right? It might be microns, it might be nanometer-sized film, but each of these layers is of some finite thickness. So even if there is diffusional behavior within the film, which is also, to me, probably somewhat unlikely, though I suppose possible depending on the film porosity, most of the diffusion is going to be taking place in this electrolyte phase, right? That's where you have an actual semi-infinite distance going on in the solution phase, in the electrolyte itself. Okay, so the Warburg should probably be here, if anywhere. Now, the other thing is that even if you had diffusional behavior within either of these other 2 layers here, right? I want to show you what the effect of that is on your EIS data. So the last thing that I'll share as a means to answer your question is in our software. Let me share that for you now. Okay, so this is our software called Aftermath. It's a bit small here, but what you can hopefully see a little bit is what I've drawn is a custom circuit here. I have a leading resistor, and then I have, basically, to your question, I've neglected the third film just to simplify things, but assume you have a substrate film, and an electrolyte, right? I have 2 Randles elements. I've put a Warburg in both of them, okay? And now, just to see the effect of that on the Bode and the Nyquist plots, and in particular the Nyquist plot. Now, most of us know that the effect of a Warburg on the Nyquist plot is this part here, right? This 45-degree slope at low frequencies. Well, I suppose what you would think, or you might think, right, is that, okay, well, if I have, let's just say I have something like, okay, I'm gonna share this screen for you so I can illustrate what I'm trying to say. So if you think about this 45-degree feature here, right, that's the Warburg. Well, if you had one in each film, if this is like, this right here is Randles 1, this semicircle is Randles 2. If you're proposing that there might be two Warburgs, then you would propose, maybe Warburg 2 would be here. So shouldn't I have like some sort of Warburg over here and then my second semicircle? So like, should this be Warburg 1? Should it show up here, right? So let me show you graphically. That is not what happens. That's not how mathematically this works, okay? So here you see Q2, Q3, W2, and W3. So W2 is that first Warburg. W3 is the second one. So the second one behaves the way you would expect. So the second Warburg tail for the second interaction, if I increase the Warburg, the tail goes off higher, right? So this is like more diffusion, less diffusion. Okay, this is a normal sort of behavior for infinite plane diffusion. As I increase the first one that's embedded in the first Randles elements, it does not make a tail. It actually kind of increases the second tail. It moves the whole thing kind of at a tilt. Like the whole Nyquist plot starts tilting up, but it does not behave the way that I proposed or just drew, that maybe you were thinking that might be the case. So what this means is that even if, let's just say, you proposed that there was such a circuit, that there was an infinite plane Warburg on both of them, first of all, it would be really difficult to tell that. And secondly, from the impedance data, it would be almost impossible to tell that, because visually, it just looks ever so slightly different. And it might get lumped in, the first Warburg, with the second, right? By changing this W and by changing this W, it almost looks like I'm doing the same thing, right? It just moves the end tail up and down. And it moves the second semicircle along with it ever so slightly. But you can't really differentiate between those two. And so part of, I think, my answer to you in the comment that I had given was that these would probably aggregate together, right? The diffusion, you might not be able to do a circuit fit and differentiate between the two, because when you do your circuit fit, you just get one infinite plane Warburg, because those diffusional effects are probed at low frequency. So there isn't a different enough time constant between two concurrent diffusion processes to be able to interrogate it with impedance very easily. And so the short answer is that, again, I don't think very likely you would have a situation with two Warburgs. And even if you did, visually, it would be very hard to tell the difference between them. And your fit would probably not reflect that, right? You might just end up getting your fit where the first Warburg is not even there. Look, I can make this Warburg almost completely gone, and it doesn't impact my data. I still have this other Warburg. So who is to say if this Warburg tail incorporates 1, 2, or 3 different diffusional sub processes? They all sort of aggregate into one. Okay. I'm not going to talk any more about that because I don't want to go on too long. I hope that's clear to you. I'm sorry, I'm forgetting the name. Was it Dev Pentacom? I hope that that addresses that question for you. If you are here, please feel free to chat, and follow up, or you can follow up on the comment section again. But hopefully that's, again, a little bit of a clear answer for you. I see that Tice, you've asked a question as well. I will get to that in just a second. There were 2 questions in this event just before I went live. I'm going to get to those now. One of them is very quick. One of them will take a little longer, but I'll just try to go chronologically here. So King of Chemicals, this is an easy question, unfortunately. How to take the values of different circuit elements after fitting EIS data through ZSimpWin software? I can't answer that. ZSimpWin is a circuit fitting program from, I think, from Amatec, which is a competitor of my company. I have not used that software. I don't know. It's not a piece of software that my company makes, and so I'm sorry, I can't help you. I can't illustrate for you our competitors' software. I simply don't know, and it's not something I can really, comment on. So my apologies there. You might have to contact Amatec if you need help with their software, or I don't know, maybe there's some colleagues or some other people who you could speak to who have used that software, but I'm not, unfortunately, able to answer for you. And then another question that came in a little bit ago was from Yusuf, who asked, could you please explain multi-sine method for AC voltage response measurement? So basically impedance is what I'm assuming here. What are the advantages and disadvantages of this method? And are there any suggestions to tackle the disadvantages? So in short, the multi-sine method, give me a moment to pull up my PowerPoint here. I can try to address this for you. Okay. So the basis of an impedance experiment is if I have some system, I can input a sine wave. So this would be some sine wave E as a rate of time is equal to some amplitude E naught times the sine of some frequency times time. Okay. And if my input is potential, my output will be current. I'm trying to draw a perfect sine wave. That this shouldn't be attenuated. I'm just not a good artist. Then the output current, for example, will be a current as a function of time is equal to some current amplitude times the sine of omega t, the same frequency, and it may be shifted by some phase angle depending on the capacitance of the system, essentially. Okay, the typical impedance experiment involves sending in a bunch of different frequencies. So you go from fast frequencies to slower frequencies to much slower frequencies, and so you'll have a bunch of different frequencies, and you go through all of them one at a time, get the response, do analysis. I'm going through this quickly here. I have a webinar on our YouTube channel you can look at if you wish. I talk more in detail about the theory of this impedance. In short, the multi-sine method is where you send a bunch of them at once. So if you were to superimpose all these sine waves on top of each other, you might get something that looks a little weird and jagged because it's a bunch of sine waves all on top of each other, and you send that into the system, and then you deconvolute the signals using a Fourier transform, and that gives you the component frequencies. Okay, so that's what a multi-sine experiment is. Now, I'll try to illustrate for you what it looks like, and it'll give you some of the advantages and disadvantages. This right here is just an Excel sheet I built pretty quickly here. You can see I've got just 3, each of these columns with different background colors here are just 3 different sine waves. So this is where I can put in any frequency. This is an amplitude and a phase angle if I want. Okay, and so the first one I have here is like, I guess like a 50 millihertz. It doesn't really matter what the exact frequencies are. You can see it plotted here. This is just some sine wave. If I change the frequency, you can see I can make the frequency faster, and then I have more, more sine waves complete. Okay, fine. Now, if I have a second sine wave, you can see, for instance, try to break down this plot here. The red is the second sine wave. The blue is the first one. So I made a second sine wave, slightly faster frequency than the first one. And the yellow is if I just add those sines together, right? Now, you can see that at certain periods in time, the red and the blue reach a maximum like at the same physical time, right? And so the combination of those, the yellow is like double, and then it's almost double the back, and then but then it kind of starts to go down because they're destructive interference. Like as the red one is all the way up here, the blue one's all the way down here, so the sum is almost 0. So you can see the yellow trace here, orange yellow trace, is when you add these together, right? And what I can do, and I could add a third one, for example. I'll make it a slower trace, right? Here's just another random one. That's a little too slow. Let's make it a little faster. All right, now you can see the yellow is just adding all of these traces wherever they happen to be. And so actually at this point here, right, you almost see all of them reach a negative at almost the same time. And so my sum multi-sine goes way far down. Now this is the first sort of disadvantage of something like this, right? I'm applying an amplitude. I just picked like the number 1, whatever this number is. But if this is like 5 millivolts or 10 millivolts amplitude, well, that the result is that my multi-sine can triple that, right? If I have 3 sine waves added together. That could be a problem. If I have too large of an amplitude applied to my system, it might start to be nonlinear. That, again, could cause issues with your results if your amplitude becomes too large. So what you sometimes do is adjust the delay of some of these sine waves. This I can change its phase delay to try to minimize how far maximize the multi-sine ends up being. It ends up being a bit of a odd situation going on. And I could also pick different combinations of frequencies to adjust the multi-sine. It's just going to be a sum of everything. The point of this is that one of the disadvantages is that if my multi-sine sum becomes crazy, it can cause issues with the result. Too high of an amplitude, things like that, right? The benefit is that I'm getting 3 sine waves out of the way at once, so it saves me time. To the best of my knowledge, there isn't a lot of advantage to multi-sine other than saving time. In theory, if you have combined your sine waves smartly enough, and the amplitude isn't too crazy, and you cover every frequency that you want to cover, you should not get a different impedance result than if you just did each frequency individually. It should be the same thing in theory. And so the only advantage is that it can just be quicker. And so if you don't want to wait 7.5 minutes for an impedance spectra to be done, and you'd rather get it done in 4 minutes or 3 minutes or something, then great, multi-sine can be useful for you. And that's not to trivialize that, because if you're doing a lot of impedance spectra, it can save time in the long run. But in many situations, I do think that multi-sine isn't necessary, simply because typical impedance spectra, unless you're going to like really, really low frequencies, doesn't take that long. Now, even if you are going to really low frequencies, you still have to have at least the time required to complete the lowest frequency, which if it's like a millihertz is 1,000 seconds, right? It's like it can still take time unless you have a sort of a program that allows you to like do partial sine wave. I think the accuracy of that starts to get poor if you don't complete enough data, like your signal to noise ratio can be a little poor. In any case, that is very generally what multi-sine is. I don't have a potentiostat here with me. I don't have the ability to like run impedance and kind of show you anything live. But that is basically what a multi-sine is. And again, to the best of my knowledge, the main benefit is that it's quicker to get a quick snapshot of a system. But most programs and potentiostats and softwares, I think, that do multi-sine measurements have the ability to like smartly pick the combinations of frequencies and phase lags and things like that, so that you don't get total blow up of the um, multi-sine amplitude like this as much as possible. But it can be tricky, right? Just fundamentally to make sure that that amplitude attenuation, making sure you have enough amplitude to perturb the system, but not so much that it's nonlinear. That process is hard enough already, let's just say, for a single sine wave, making sure. Now, when you have multi-sine, you're dealing with it to a higher level, and so it requires more care. But that is my best sort of explanation of multi-sine, and to the best of my knowledge, some of the pros and cons that are come with it. Okay, I'll try to get now. Let's see. So there's a few questions that have been asked live. Let me take a look here. So Tice has asked, is the open circuit potential the potential where there is no electrical charge in the electrode? If so, how do you measure the open circuit potential? The open circuit potential is the potential where yes, I think I guess that's an explanation. It's the potential where there's zero currents. So it's a thermodynamic equilibrium phenomenon, and so when you have two electrodes in solution, for instance, they will equilibrate, and there will be a potential at which there is no passage of current between the two. And so just the word charge in what you add, it's more like the current is equal to zero, I is equal to zero. Charge, I don't know if that's necessarily true. Charge is more of like the aggregate of current over time. The strictly speaking, open circuit potential is where current equals zero. And so how do you measure it? Well, I mean, practically you use a potentiostat, you use a multimeter. A multimeter is a more direct way to probe the potential between two things, right? I mean, if you're familiar with electronics at all, you might be familiar with voltmeters or multimeters. The key is that there is, with a potentiostat in particular, for instance, you're measuring the potential across two electrodes, and the potentiostat often does a thing which is called, it disconnects the counter electrode. And by disconnecting the counter electrode internally, no current can flow. No current can physically flow from between the two electrodes, and so all you're doing is measuring potential. There's a lot more to this as far as physically what's going on, right? I talked about some of this. I just gave a webinar a few months ago on potentiostat operation. I would encourage you to check that out on our YouTube channel if you want to know how a potentiostat, the schematics and the electronics and how it works, to get into a little more detail about that. But basically, you're measuring between two high impedance sense lines, so no current can flow, and you're just directly measuring the potential where there's no current. And Chris, good to see you again, Chris. That's right. Chris says it's an open circuit, no current flows, right? So no applied bias and no current is flowing. That is correct. Okay, so moving on, I see Ricardo has a question. What is the best possible way to increase the hydrogen collection in a platinum ring in the RRDE? So this is kind of a question about collection efficiency, right? So collection efficiency is the phenomenon by which something generated at a disk goes over the ring, and then you detect it at the ring, right? And so increasing the hydrogen collection in a ring, or just basically improving your ring's response, is actually a function of geometry entirely. Okay, let me bring up a PowerPoint to kind of illustrate this principle here. I have another webinar I've done on RRDE, and I have an illustration of collection efficiency. I can show you this, whether it's for you, Ricardo, specifically, or for anybody else who might be interested. Let me do this here. Okay. Share my presentation. Okay. So just as sort of, again, maybe for you, Ricardo, this is something you understand already, but I'll go through this pretty quickly to describe collection efficiency. So when you have a rotating ring disc electrode, you have a disc, might have a film on it, and you have a ring that is concentric, with the disc, and there's a separator between the disc and the ring, something like Teflon or PEEK, some insulating polymer. Okay. We rotate our electrode and we draw solution and reagent towards the electrode surface. This is the rotating ring disc electrode experiments, right? If these blue dots are water or some molecule, let's just say there's some molecule, for instance, that can be reduced, right? So I hold my disc at some minus potential. So whether this is specific to your hydrogen question or not, right? Just the concept is hopefully clear. I turn blue to pink by holding my disc at a negative potential. And so as I'm spinning my electrode, the blue dots, reagents, hit the disc and are immediately reduced to the pink species. And then they're going to be swept away. Well, at the same time, I hold my ring at a positive potential. And what that will do is, this is sort of the question of like increasing a hydrogen collection or collection at the ring. So as the pink dot sweeps over the ring, because the ring is at a positive potential, it gets reoxidized back to the blue. But the problem is, of course, not every pink circle will reach the ring. Some of them may go off at some angle like this. And if that happens, it doesn't get reoxidized. And I don't measure it, right? I'm not measuring it at all, because if it doesn't hit the ring, it doesn't get reoxidized, I don't get my potentiostat response of my current, or my current measurement basically from the ring. Okay. It's actually theoretically, now practically is a different situation, but theoretically it is completely dependent on geometry. Okay. So it's a very large equation, but effectively it matters the disk diameter, the ring thickness, and the distance of separation between the disk and the ring. Empirically, we measure it by just measuring the current at the ring and the disk. Okay, and this is the collection efficiency. Okay, so a couple things. The direct answer to your question: get a thicker ring. Okay. The second answer is that it doesn't matter. If your collection efficient, let's just say a typical common collection efficiency of an RRDE tip is about 25%, maybe 30%. What that means is not that you need to get that it matters if you have a disc, a ring that has higher collection efficiency. It just means that you have to use a different factor to correct your data. So what that means is if I get 25 milliamps, that's too high, 25 microamps, okay? I get 25 microamps on my ring and it's 25% efficient. What that's telling me is that I actually should have 100 microamps of current, but I'm only measuring 25% of it because of the geometric limitations. If my ring were thicker, I would get, let's say, 35 microamps, but I still should have 100 because that's like, in theory, the perfectly efficient situation where all of those pink blue dots, hit the ring and got reoxidized. You would get all the hydrogen collection or whatever you're trying to collect on the ring and detect. It doesn't matter because the 100 microamps in this situation, this example, is the correct answer. So when I get 25 microamps, I divide by 0.25 and I get 100. When I get 35, I divide by 0.35 and I get 100. No matter what, my corrected ring current is still 100 microamps. So collection efficiency is something that, unless it's so small, like my ring is so thin or it's not picking up anything at all, maybe it needs to be polished, maybe there's other mechanical problems. It actually doesn't matter what the collection efficiency is because it's just a factor you're correcting the ring current by to get the amount of current that would have occurred in a perfect system, okay? But again, practically, if the distance between ring and disc is smaller, if the ring is thicker, these are all ways that you would increase the collection efficiency and you would improve the collection on your ring of whatever you're collecting, right? Detecting on the ring. But ultimately, I hope it's clear. It really actually doesn't matter because you're just correcting that current afterwards. All right, we have a Mott Schottky question from Afreen. How to extract the depletion width from a Mott Schottky plot? That's a good question. I actually, I'm not sure if you can do that. So the Mott Schottky equation, let me sort of share here. So just to be clear, the Mott Schottky equation here, zoom in so we can kind of see it a little bit easier. I think it's in the screen here. So you're plotting 1 over this one right here. You're plotting 1 over the capacitance. This is the space charge capacitance. Okay. And we have basically dielectric constant, the permittivity of free space, the area, fundamental charge of an electron, the potential, flat band potential, donor density, Boltzmann constant temperature, and the elementary charge again. So it's not here, right? This is the bulk surface area of the electrode. I'm not sure if there is a direct way to get, this is actually a good question. If there's a way to get the depletion width, and I'm not sure what you mean by depletion width. Do you mean like the thickness of the space charge region, or the Helmholtz, the inner Helmholtz plane, or the diffuse region? I'm not sure what depletion width is in the context of Mott Schottky. I would have to look into this a little bit more. This is in a situation where if I had my partner in crime here, I have a lot of sort of resources and publications on Mott Schottky. I could try to look through, but I can't do that when I'm by myself. No one can cover and answer a different question while I investigate my sources to try and answer your question. In short, the things that you get from a Mott-Schottky plot are the donor density of your N or P-type semiconductor and the flat band potential. But beyond that, I'm not 100% sure. And also, again, I'm not 100% sure what depletion width is, if this is related to the space charge region or the out in the electrolyte, the Helmholtz plane or the diffuse region or something like that. I'm not sure which exactly of those widths you're trying to determine. But again, without someone without a little more investigation of some literature, I'm not sure I know the answer to that right now. Let's see here. Cross Heat Hero has a question: how to decide the potential range for a CV or LSV experiment? What will happen if I set the potential range too high? So this is one that we've answered a handful of times. My colleague Alex usually answers this, but I can try to address it for you. So let me draw some things here. So if you're doing a CV or an LSV, right, you're looking on a potential axis here and a current axis here, right? I'm going to assume an aqueous system, so we're in water, okay? At the extreme positive end, so extreme positive, we have oxygen evolution reaction. And at the, if I can draw properly here, right, at the extreme negative end, we have the hydrogen evolution reaction. Okay, so you may be familiar with these. Now, I bring these up to say that these are kind of the bounds of, like, the absolute bounds of your experiment ultimately, because if you go way too high, one of the answers to your question is that you will start ripping apart the electrolyte and producing oxygen. On the other hand, if you go too low, you will start ripping apart the electrolyte and producing hydrogen. Okay. But ultimately, what you're looking at is that you probably have some reaction you're trying to study, right? You have A plus an electron goes to B, something like that. Now, this may have some E0 associated with it, right? E0 is equal to N volts, whatever. Okay. So what you're trying to do is study this. Now, in your voltammogram, what you're trying to do is find a window where you can observe that process, right? So often what you'll do is, if you know that this E0, let's put a number to this. Let's say, let me erase this. So let's just say this is 0.1 volts. Okay, let's just make up a number, right? And let's say that that's right here. Okay, so what I can do is I can just do my LSV or my CV over this very short window, something like that. Well, maybe I don't even get quite, all of this. Maybe I just have, like, I don't get a full resolved thing. So I pick, like, this is my first window between, like, 0 and 0.2, just around that E0. Okay, well, that isn't enough to see what I really need to see. So then I decrease by a few hundred millivolts and I increase by a few hundred millivolts, and I do it again. And now I scan and I see my peaks, and then I can keep on increasing and decreasing my window a little bit at a time. And eventually, as I do that, when I scan negatively, it's going to start to shoot down. And as I scan positively, it's going to start to shoot up. Right over here is the OER, and over here is the HER. So this is the danger when you are trying to find that window, right? Is if you go too far negatively, you're producing too much hydrogen. If you go too far positively, you're producing too much oxygen. Okay. The other danger. So to that point, you want to try to cut off your upper potential just before you go crazy, and cut off your lower one just before you go crazy, right? That would be one way to sort of do that. The second answer to your question is that there's an added danger of going too high in potential, especially, for example, if you have like a glassy carbon electrode or a carbon-based electrode, is that too high of a potential can oxidize the electrode itself. So while you're using glassy carbon, let's just say, or some carbon paper, some carbon-based electrode to oxidize or reduce your species you're trying to study, if you go very, very, very positive, the substrate, the carbon itself, can start to oxidize, and then you can get into some real problems, right? So that's the caution, is that you want to be very careful, especially with certain kinds of electrodes. When you go very, very high in potential, be careful to increase slowly so you don't damage your electrode itself. Because again, that can be something that can happen. In addition to the OER, which can interfere with your electrode, it can produce bubbles on the electrode, things like that, right? So some of those things are to be you want to pay attention to. So I hope that's useful for you, Cross Hero. Let's see. Anurag has a question. I see, Krista, you were helping me out here. I appreciate it as always. And let me read his question, and then Chris, you were asking some follow-ups. I'll see what's going on here. So how do I design an H cell to perform photoelectrocatalytic reaction for CO2 reduction so that CO2 passed in it doesn't get leaked? And Chris followed up to ask a good question. Are you looking at an aqueous system and looking to dissolve CO2 into the electrolyte? That's what it seems to me, Chris, as well. That's kind of that's how I took it. Yeah, there's let me try to bring up something here. In short, you need, let's see, if you're doing CO2 reduction, very possibly you are also looking to sample your cell, I guess, into a GC or an MS maybe. So it's not easy to like completely seal the system in that way. You have a little bit of a trickiness there. For example, there's some cells like this one. This is just kind of one example. This is called a separated cell. You can see sometimes they involve a membrane, right? And in this case, this cell has like a flat. Well, I guess one of the answers to your question, I know I'm kind of scattered here a little bit, apologies, but one of the things that's really needed when you're doing photoelectrochemical is a flat surface. You see how the end of this is basically flat. It's a rounded, cell. There's a membrane clamp here. But this being flat is necessary. So if you're doing photoelectrocatalysis, you're probably illuminating and shining a light somewhere. And if you're shining a light through a curved convex piece of glass or quartz even, the light will refract very likely. And so it's usually a good idea to make sure you have at least one surface that's flat, made of quartz, because quartz is more optically transparent. And so that's the first thing about getting that. Now the leakage, this again, I'm just sort of showing you something that I make here, but we have these kinds of caps. So what you want is something usually you need O-rings, and this particular example here is like some sort of a, not a manifold, just you need some way to cap and make sure there's only one in and out like port, and then this is a kind of a cap system that that allows you to plug the holes with whatever you want. And so one of those things is a gas inlet. You can plug it with a tube. Sometimes you can use a like a septum and then use a syringe. The septum reseals. They're not going to seal perfectly and all the time, forever. A lot of times with these things like O-rings and rubber gaskets and things will seal pretty well, but they won't seal like absolutely forever. So you have to just be aware that after some period of time, it might you'll have to replace the O-ring or something like that. And thank you, Chris. What you just said is exactly what I was going to say next. One of the other things about carbon dioxide is that it is carbon dioxide, and generally speaking, a lot of gases are like this, but carbon dioxide, if you look at like what's Henry's law, right? It's more soluble at in cold solution than in hot solution. So one of the tricky things about doing CO2 reduction in these kinds of systems is you want to try to cool down the electrolyte or the cell itself if you can, because it will dissolve more CO2, and that can improve the amount of CO2 you have available to reduce. But generally speaking, you're looking to have some kind of a cap or system where you can seal a gas inlet as well as your electrodes, so that you can pump CO2 in, but have everything sealed with a rubber gasket, right? And then you maybe have one outlet that you can control, maybe with a valve, or send it to a sampling system like a gas chromatograph or a mass spectrometer, something like that. So those are a couple of I don't know, suggestions to you, I guess. We, like I'm showing you here, a couple of cells that my company makes. There's a lot of different pieces of types of glassware you can do. But again, the main things for you, because you're talking about photoelectrocatalysis, is to make sure you have a flat surface made of quartz or a window made of quartz that you can shine your light through, and direct it how you need to. If it needs to direct it at the electrode or something like that, make sure you have that ready. As well, try to get some method of sealing O-rings, something like that. That's why the cells that a company like mine, or really some other companies make, there's set taper ports and everything. It makes it easier to seal, right? If you just have an open piece of glass, what's the size of O-ring to seal it? Does it seal well enough? Some of those things are tricky. So that's why standardized size is 24, 25 ports, 14, 20 ports, septum, those kinds of things. The standard sizes will seal a little bit more regularly than just a homemade system, because homemade systems are what people use a lot for CO2 reduction and for things like, um, separated cells and membrane cells. And the tricky thing is that getting them to seal doesn't always work the way you want. Moving along here, there's a question from Simone. Do you have suggestions on how to build up a 3-electrode setup cell for the observation of HER, hydrogen evolution reaction, and what should be avoided? I'm going to use a nickel mesh. How can I determine its surface? Okay, so first of all, doing any experiment that involves HER or OER, but it's really the generation of gas, is going to be tricky. You're generating gas in a liquid system. The gas can break up the liquid solid interface. So there's something fundamentally tricky about that for sure. Just to be clear, there's sometimes people, if you can sometimes stirring the solution, a lot of times if you're doing a nickel mesh, it's not exactly the same thing. But I talked about RRDE earlier. Sometimes people will do rotating experiments. It can help because as you're rotating, it can help fling the gas that's made away quicker. Like if the solution is moving, if you have a stationary system, gas can build up and it can basically lower your effective surface area. Over time, if the gas doesn't escape, that's tricky. And if you have a mesh, it can be even trickier if you need really precise measurements, because bubbles can get trapped within the mesh, and then your surface area is sort of variable over time because gas is breaking it up. So that this is tricky for sure. As for if you're how do I determine the surface? I assume you mean like surface area. If you're asking how to determine the surface area of a mesh, people do things like there's a technique called BET. It's not an electrochemical technique. It's called Brunauer Emmett Teller. It's a nitrogen adsorption desorption isotherm procedure. I had one in my research facility when I was in graduate school. It effectively is a measure of the surface area per gram of a species. You put it into a little, vessel, and you put it in, and it runs a program with nitrogen gas, basically. I'm not describing it super well, but the point is that that's one of the ways that is done. To measure electrochemically active surface area, there are methods to do that electrochemically. The most common one is with like platinum hydrogen, but basically you need to know the specific the area specific charge associated with some process. And for nickel, I don't know what you would use. So you might have to look into the literature of this a little bit. If you're trying to find like the electrochemically active surface area of your mesh, for example, you'd have to know like how many coulombs per centimeter squared some process on nickel fundamentally has, and then you can like measure yours, correct it by that, you'll get area out of that. I know I'm sort of being a little bit vague here, but I don't have any better answer than that, unfortunately. Okay, so I think of, so what to be avoided. Mainly it's the generation of gas. If there's a way for you to like, it depends. Let me just put it, the last thing I'll say about it is, let's say, it depends what you're after. Are you trying to just like generate hydrogen and just see how efficient it is over some time? You're just trying to blitz hydrogen into it. Okay, fine. Or are you really trying to get like precise electrochemical measurements? If it's the second thing, if you're trying to get precise electrochemical measurements, you're going to want to try to find any way you can to get rid of the gas, like I talked about, stir the solution. Maybe periodically you have to like move the mesh up and down to try to free gas out of it, something like that. If you're just trying to generate as much hydrogen as you can and see how well it does, a lot of times you're just going to not care about some of those other things. You're just going to send a bunch of current through it, or set it at some negative potential and see for a while how much current you get. And if it's inaccurate, it's not that big a deal. You're just trying to see like very roughly how much hydrogen it can produce. So these are kinds of different approaches. You'll find a lot of stuff in the literature on HER. There's different approaches, right, with different levels of accuracy and things like that. But anyway, I think I've talked through this enough for now. Feel free to have a follow-up question if you'd like, Simone, and I hope that at least, I don't know, gives a little bit of context for these types of experiments. Let me see here. I think there was a follow-up from from Ricardo from Twitter here. Ricardo had asked, so let me remind myself what you asked originally. I'm answering a lot of questions, trying to remember here. You had asked, right, the collection efficiency on platinum ring. It looks like you had a follow. I don't know if it's a follow-up question or just a separate question. Let's see. Was how could one minimize the diffusion of hydrogen bubbles onto the solution from the disk in RRDE? Okay, so that's kind of like what I was just talking about a little bit. As you're rotating, sometimes that fixes it. Sometimes the problem is if the bubble is like perfectly centered as you rotate, it won't like fling off. If it's off center, a lot of time you'll see the bubble sort of do this and then it flies off. One thing that's it's hard to do practically, but I've had some of our customers as we sell RRDE equipment. I've had some people do this kind of thing where they take the shaft of the rotator, get out of my face, and they tilt it. So if you can find a way to sort of engineer this, it's hard because you got to make sure everything is fixed and not gonna bump and break, right? Getting tilted systems is not easy, right? And it's not even easy for us to manufacture it this way. But I have seen people, some customers have somehow managed a way to do this. If you can get the shaft tilted, as it rotates, because it's at an angle, gas that's formed can escape more easily. So if you have a way basically to get some kind of an angle of your electrode, that can also help gas. Right, gas is going to rise in the solution, so it has a place to escape. Otherwise, to a certain extent, if you're at a potential that generates gas, you can't stop gas from generating. It just isn't possible because that's the goal of the experiment. It's like, I wish I had better advice, but for the most part, if you're doing an experiment like OER or HER, generating a gas to study it electrochemically on purpose, you can't escape the gas formation because that's what you're doing, right? This is just a common thing. The other thing, I guess, the last thing I'll say is that sometimes gas forms because you're at a high temperature. If you're doing like 80 degrees C or something like that, sometimes what happens is if you, let's say you get your stuff in your solution, you connect your circulator and you set it to go to 80 C, and then you start spinning and doing your electrochemistry, you'll get bubbles to form onto some parts because not everything has equilibrated to the high temperature. And so you have a high temperature solution from your circulator touching maybe an electrode or a shaft or something that's not, it hasn't, like, it has a different heat capacity, right? It hasn't gotten to that temperature yet. And so you have hot temperature touching cold temperature, you get a bit of localized kind of uh, uh, condensation or whatever what the right word is here, but bubbles can form because of a temperature mismatch. So if you're doing elevated temperature tests, make sure everything in the solution has enough time to get to the same temperature and equilibrate. Especially if you have tubes like Lugan tubes or isolation tubes as well, because bubbles that form in those can be catastrophic. All right, there's a couple other questions here before. Let's see, Chris was talking about CO2, of course. Now, okay, so Eunice asked a question, what does the thickening of the double layer region mean in cyclic voltammetry analysis? Thickening of the double layer region mean? It means you have a higher capacitance, for one. So let me share a thing with you here. So I kind of, again, I've sort of assumed from your question, you're talking about like if you have a cyclic voltammogram, right? Here's my current potential. Here's my current. So if I have, if I do a CV, whether I have something Faraday or not, whatever, but if I had thicker sort of band between the positive and negative, sections here, right? What does it mean? Well, it means one of a few things, right? The thickness here, this is a current, right? The thickness, right? It's actually on the y-axis, so it's like it's a current value, is proportionate to the capacitance. Okay, so the current, is equal to the capacitance times the scan rate. Sorry, my mouse is not working so well, so I'm drawing terribly. So I think that's correct. Volts times farads. Someone correct me if I'm wrong. I think this is correct. This is one that I, for some reason, always have trouble remembering. In any case, as the current goes up, the capacitance goes up. So another way to say that is that if my thickness is, if it's thicker, it means that I have more capacitance. The double layer is just thicker, right? So sorry, I'm just checking here. Amps, coulombs over volts. Yeah, I think that's correct. So okay. So another reason for a thicker band is that a faster scan rate. If you scan faster, you will have a thicker. You'll charge the double layer up more. So I think as a hopefully a quick answer to get to some other questions here. Those are the two things that are the most obvious answers to you. One is it just means I have a stronger capacitance of non-Faradaic double layer buildup. And the other is that I could have a faster scan rate. So if my scan rate goes up, I'll have a bigger current here as well as you scan faster. Okay, let's see. Going down the line here, Snehasis says how graphene oxide is prepared for fuel cell. So I guess I don't know if you're asking how to make graphene oxide or how to make a fuel cell setup, like it's called MEA, membrane electrode assembly. I don't know how graphene oxide is made, like synthesis process. I don't know. I haven't made graphene oxide before. That's prepared for a fuel cell. So I could talk about making an MEA, making like how a fuel cell is constructed. With it to a certain extent, I can explain that. But I don't know if you're asking. It looks like you're asking how graphene oxide is made specifically, and I don't know the answer to that question. So, or I can't. I don't know. You could probably find in the literature, processes for synthesizing graphene and graphene oxide and all kinds of materials, and that's unfortunately not something I have experience with. If you're asking about MEA fabrication in fuel cells more generally, please clarify. I can talk about that, but I'll move on for now because I'm not sure if that's what you're asking. Okay, let's see. Where did I answered Ricardo. Arturo has a question. Let me see here. For polishing and polymerization, is there a maximum number of cycles one can perform? Polishing and polymerization. How can we know when we are reaching a maximum cycle limit? So I guess polishing is the word that is confusing me a little bit. I assume you're asking about like cleaning via cyclic voltammetry. That's what it looks like, but polishing is obviously a physical process where you're physically polishing the electrode. So I assume in polymerization, polishing and polymerization, there's a maximum number of cycles one can perform. I mean, again, I'm going to have to just make an assumption that you're talking about like cleaning an electrode surface with cyclic voltammetry, just cycling back and forth. In general, no, there is no limit. Like again, one of the assumptions I'm making is that the experiment that you're referring to is you have an electrode surface, you've done some tests on it, and then you try to clean it or get it wiped fresh. And so you will excuse me, sorry, I got distracted for a second here. Glassy carbon. Okay, so you're cycling glassy carbon back and forth. And if you're within a window where you're not going to damage the glassy carbon, like fundamentally, you're not going like so high and so low, and you're cycling and you are like waiting for it, yeah, electrochemical polishing. Okay, so you're cycling. So generally speaking, no, not really. It's just that there isn't a need to go forever. Like you can make it do 1,000 cycles, and it should just keep repeating on itself. Like if you don't push the potential so high that you're going to damage the glassy carbon itself. If you're just cycling glassy carbon in acid, like you could just. I mean, it's nothing. I mean, nothing's going to happen practically. And I guess if you're sort of thinking to yourself like, okay, well, I'm trying to electrochemically clean my glassy carbon. I just kind of want to set it, to scan for an hour or a few hours and go do something else, but I don't want to overcycle it. You don't have to worry about that being a problem. I don't think. You can set it to go for a long time and check on it every once in a while. And usually the procedure for this, people will do 100 cycles or 50 cycles. It usually doesn't take that long, but it just depends how stubborn your electrode or your adsorbed species are or something. Yeah, just set it to go for a long time, back and forth. And as soon as it's tracing on itself, you can stop it. But if it does that for a longer period of time, nothing's going to happen. It's not. It shouldn't negatively affect the surface. I wouldn't worry about that. Okay, let's see. Chris, you were talking about some of the diffusional stuff and everything. Does anyone build an ultrasonic electrode systems to eliminate bubbles on the surface? That's a good question. Ultrasonic electrode systems. Gosh, that's a complicated question. I don't think so. I'm not even sure what an ultrasonic electrode would look like. Like what would its geometry? You know what I mean? Like would it have to be small, or is the electrode itself connected to, like a sonication so that it's like vibrating and something like that? I guess the tricky thing about that is what would be the flow patterns and the diffusion. Yeah, that's a good question. I don't think anybody makes something like that, first of all. But if they do, um, gosh, I don't know what it would look like. But it's a good question because maybe you would avoid, microscopic bubbles if you could do that messing with your system. Let's see here. Rasmi has a question. Please explain about harmonics and THD and nonlinear EIS and why we need to do nonlinear EIS. Oh boy. THD. What is THD? THD is what? Total harmonic distortion. Okay. So, first of all, I have a bit of a sore spot for the concept of nonlinear impedance. It's not something I've done myself, and I don't like it because it fundamentally violates the rules of impedance. One of the fundamental rules for impedance spectroscopy is that it must be linear. So even just the term nonlinear impedance makes no sense. It's like saying a married bachelor. You can't both be single and married at the same time. Like it's a contradiction fundamentally. So now that isn't to say that nonlinear impedance or a, let me say it this way, nonlinear electrochemistry experiments, nonlinear perturbations, whether sinusoidal or otherwise, aren't potentially useful in getting information. I suppose they can be. That's probably perfectly reasonable. But I very much do not fall in line with the concept of nonlinear impedance. I can't get there. I don't fundamentally agree with its existence. Impedance requires linearity, so nonlinear impedance just doesn't make any sense to me. And further to that point, unfortunately, I can't speak really clearly to its analysis and the, I guess, harmonic distribution and things like that. I can't speak more heavily to it, and part of the reason is I don't have a lot of experience with it, and part of the reason is that I fundamentally disagree with its existence. So unfortunately, I think I have to sort of leave that question there. Let's see. Preeti Yadav has a question. I did the CV of conductive carbon-based ink. The S shape with no oxid. I'm trying to understand here what you're saying. Okay, so the S shape with no oxidation and reduction peak. With the same procedure, I did CV of sensor and obtained a duck shape plot. Try to understand what you're asking here. You did a CV of a carbon-based ink with an S shape with no oxidation and reduction peak. In the same procedure, you did a CV of sensor and obtained a duck shape plot. I guess I don't know how. I don't exactly know what you're asking, and I don't exactly know what how I can help. It seems I guess I'd have to know more information. I mean, when you get an S-shaped plot, it usually means you have some diffusion limitation. If on the oxidation and the reduction side, if you have some S-shaped, it usually means there's diffusion limitation, which usually can only happen if you're rotating an electrode or you have a microelectrode. That means that you're not getting an increasing diffusion layer thickness, and I don't know anything about your system excuse me, that is causing that kind of behavior. I would probably need more information. With the same procedure, you did a CV of sensor or sensor. I don't know if that's a specific product or you're trying to say you did a sensor experiment and you got a duck. With the duck, there's diffusion limit. You're getting, if you have a normal duck, then you're getting, kinetic effects and then diffusion layer growth and like a normal voltammogram. I guess I don't totally understand what you're asking. Here, so I apologize, and I might need to know more about your experiment specifically to kind of understand like what's your question and what is going on here, because this is a bit it's a bit like it's not quite enough information. I'm sorry. Okay, so Rasmi, looks like you have a follow-up on the nonlinear EIS. EIS won't tell you the behavior and changes in the nonlinear region. No, that is not true. So for instance, if you're referring to, for example, a voltammogram, right? Again, I'm making sort of a simple assumption. If you have a system Faradaic process you're trying to study, right? I'm such a bad artist, so my apologies if this doesn't look very good. Let's just say you have some voltammogram like this. Well, if you're saying to me, well, I can't study, can I study this with impedance? It needs to be linear, so I have to like pick this region or this region, and I can't study here, the peaks because it's changing. Well, that's not true. You can set the potential anywhere and then just take a very narrow slice, and when you zoom in on a very narrow slice, even if it's ever so slightly not linear, as you zoom in and decrease your amplitude, it does effectively become linear. So you don't have to do impedance only at the open circuit, and then where you're trying to study the Faradaic reaction, you can set your potential there and take a small amplitude, and you can still study in the sort of quote unquote non-linear region, which I'm guessing you're sort of referring to just where there's some Faradaic processes occurring. You can absolutely study those with impedance. What you can't do, I suppose, is sweep the potential over a wide range in that nonlinear region and study that through impedance. That's true. And if what you're referring to, the nonlinear, quote unquote nonlinear impedance experiment, is such that it's sweeping, over this whole wide voltage window, well, then again, my response is sort of like, sure, that's like just doing a CV, or it's just doing a different kind of experiment. And there's nothing wrong with sweeping the potential over a nonlinear region to get experimental analysis for it. I just do not accept the premise that that experiment is impedance. It is not. It's something, but it is not impedance. And I don't agree with the analysis that is done from an experiment like that, modeled like impedance data with Bode and Nyquist plots and Fourier transform and things like that. I disagree fundamentally. It is not appropriate. It's not impedance data. There may be other kinds of analyses that you can do perfectly fine, but not impedance, unless the amplitude is small enough that it is truly linear, or at least close enough to linear at those set potentials. And sorry, there's another follow-up here. You've said in tough coatings like epoxy, you must have to do impedance with high amplitudes, which will be nonlinear region. Can you avoid characterizing materials nonlinear? Yeah, I understand. So in epoxy, with a coating, the problem that you're running into, of course, is that you have a high impedance. And so the impedance follows from effectively Ohm's law, right? So if you think E is equal to IZ, V is IR, this is basically Ohm's law, right? As my impedance goes up, my current response goes down. And so I have to increase my amplitude so that I can get a reasonable current response, right? And so as you increase your amplitude, you start getting nonlinear. I understand this problem for sure. How can you avoid characterizing material nonlinear behavior? For systems that have really high impedance, let me try to think this through. There is usually still a sort of sweet spot where you can increase the amplitude to get just enough current, but it's still linear. But if that just isn't the case, then honestly the result might just be that you can't get accurate impedance data. And to a certain extent, the practical reason is that as your impedance becomes too high, what you're actually doing is you're approaching the measurement limit of the potentiostat itself. So potentiostats have what are called accuracy contour plots, and it is basically a summary of where the potentiostat can accurately measure. And every potentiostat has some practical upper limit. It just can't measure above a megahertz or a gigahertz or whatever the number is for that potentiostat. But if the impedance is that high, it means the current response for any amount of potential perturbation is just not going to work. And so for some system like this, again, just to repeat, you can apply some potential, whether it's linear or not, and you can get a measurement, a current response. You can get possibly some sorts of analyses. But if at a certain potential or within a potential window, the only way to get a measurable current response sinusoidally, because the impedance is so large, is to make the amplitude really big such that it is nonlinear, then you just cannot do it. I mean, you can, but your results are not valid impedance. That's the harsh reality of this kind of situation. You would have to try to probe it at a region where it is linear, or try to get a more sensitive measurement, or try to boost the conductivity somehow so that the resistance, the impedance goes down so you can measure it a little bit more easily. A lot of the kinds of experiments where people test coatings like coatings on paint where they have really high impedance, very often it's just capacitive behavior. There's nothing Faradaic going on. And so very often when you see people reporting their data of really high impedance coatings, like what you're talking about, it works because there isn't really a nonlinear section. It's mostly just non-Faradaic capacitance stuff. So even if your amplitude has to be pretty large, it's still pretty linear. Like even if you do like 50 millivolts or 100 millivolts amplitude, it's still linear because if there isn't anything Faradaic going on, it can still be linear. So to a certain extent, that's the saving grace of these kinds of systems where there's really high impedance that makes this difficult. But again, I just want to kind of hammer that point home. You can probe a nonlinear region of an electrode, no problem. It's just not impedance. It's just not fundamentally impedance data if you do so. Okay, let's see. NVS Praneeth says, I am new to electrochemistry, actually photoelectrochemistry, from bias-free photocatalysis. Still somewhat confused with what exactly open circuit voltage signifies in a photoelectrochemical process and how to do it. Let's see, how can I say with a photoelectrochemical process? So we talked about open circuit potential. I don't want to get too sort of, talk about a lot of overly generalized things here. So let me think the best way to answer this. So the open circuit potential, right? Of course, we talked about this earlier. It's like a thermodynamic quantity between two electrodes where the current is equal to zero. There's no current flowing. It's where it's a measure of the potential between two electrodes, with and that's it's it's an energy state effectively. And so with light involved in photoelectrochemistry, for example, if you have light shining on your system, on your electrode, versus it's in the dark, you might get a different open circuit potential because the thermodynamics, the actual energy state of your electrodes and of your system can vary depending on whether there's light shining on it or not. And that might mean that there's, some fundamental process that can or can't occur under illumination or in darkness, for instance. So what it signifies, I mean, I don't know. I'm trying to think if there's a better way to sort of say that. I mean, what it signifies is the point where there's no current passing. It's sort of your baseline. You can almost think of it, right? So, like I don't know if what you're doing, right, in terms of photoelectrocatalysis is something where you're trying to like draw energy from a system or something like that. So like, like if you're thinking about it in terms of like a fuel cell, it's like your open circuit is where there's no current flowing. And when current is flowing, you're getting energy from your device, which is like a good thing. It's what you're trying to do. So if your open circuit potential is really high, I can lower it and start drawing current from my device and get energy, power my device or whatever. But if my potential's low and not very high, I can't get as much energy out of it or power or anything. So, you might have something where it's like your open circuit potential is 0.5 volts for whatever system you have. And then when you shine a light on it, it's 0.9 volts. So it's like there's more energy, there's more potential, electricity and power that you can get from it because you have 400 more millivolts work with, basically, something like that. That might be applicable to your system. It might not. I'm just sort of that's the best way I can think about it, maybe. So Chris says that's related to the species present. Yeah. So I mean, under illumination or not, you might have. Again, it's a thermodynamic thing. Like, so if there's some species that is present or generated on the surface under illumination or not, and that species is oxidized or reduced, like there's more energy you can get out of it versus not. And then if it isn't something you're trying to get energy out of, you're just trying to study sort of in a general sense, the open circuit potential might be where you would start a CV, for example. So it's like in the dark, my OCP is here. Well, I want to sort of start scanning up from there and back and return to my zero current spot. And then when I start shining light, my OCP moves over here. And so I want to do my voltammetry from that new starting point, because that's like my baseline. So a lot of times the open circuit potential practically is somewhere from which you base your experiments like voltammetry on, things like that. So Chris also says you probably want to characterize OCP versus short circuit dark current, or light current. So I mean, generally speaking, as a photoelectrochemistry experiment, you're trying to characterize how things change, whether there's light shining or not, fundamentally, because if you're doing photoelectrocatalysis, the application of a light should change something, usually for the better. I mean, you're trying to induce, a photon can, for example, provide energy to move an electron from the valence band to the conduction band and improve the conductivity. Maybe that's what you're doing, maybe not, I don't know. But in any case, I hope that's at least talking through this to a certain extent here. I see a follow-up. If under illumination there are more electrons are accumulated on the electrode, we should see an increase or decrease in OCP. I'm not sure how it relates to OCP. I mean, in theory, what you're saying is kind of what I just said, is under illumination, there's more electrons on the electrode. You're basically the energy from the light is providing the energy to move electrons from the valence band to the conduction band, which is where conductivity would increase. I don't know exactly if there's a correlation between conductivity and open circuit potential. You would see a decrease potentially in the decrease in the resistance or the impedance, but I don't know if how that would exactly change the OCP. If the movement of conductivity under illumination, or the freeing of electrons in some fashion, cause different species or different reactions to be able to take place that couldn't before, then the energy associated with those processes could adjust the OCP. But I don't know. It probably would depend on each individual system, to be honest, whether you would expect it to increase or decrease specifically. That would be something that probably depends on what you're studying exactly. There was a question I didn't want to miss from Hob. Let me see here. What is the equation for OER? I was assuming it was at the bottom of the duct as oxidation of oxygen from water to oxygen gas, zero charge. It's the oxygen evolution reaction is an oxidation process, so it wouldn't be at the bottom of a duct. I should clarify. I'm talking about the IUPAC convention, which is where positive potential and positive current is oxidation. And so if you're talking about the bottom of a duct, you're talking about like more negative potentials and more negative currents, bottom down. Those are reductions. And so that's not what that is. The oxygen evolution reaction depends on whether you're an acid or base. The acid reaction is the most common one, but let me let me get. I can just pull up a thing. I could write it. If I can't get it here, I'll just write it out for you. There's a lot of different. I want to try to find a good summary here. I've used one before. I've also. Okay, let me share my screen and show you the equation. It depends in acid or alkaline. OER. Share my screen. So you can see here. Try to. Just want to this chart here. So OER is this one, right? So these are the equations. So in acid, it's water, 4 electron. It's the opposite of the oxygen reduction reaction. Basically, two waters go to oxygen and protons and electrons. And in alkaline, it starts with hydroxide, and you get oxygen and water, 4 electrons. Check your question again. What is the equation? So, and this is what happens at the extreme positive end of like a voltammogram, for instance. I've talked about the mechanism before. It's basically a 4-step mechanism, 1 electron at a time, basically, is released, 1 proton, 1 electron at a time. But these are the equations for the OER, and it takes place at basically the positive most potentials. Maybe you were thinking of this one, an aprotic electrolyte. Let's see, because you were saying it's the oxygen 2- from water. So this doesn't. Excuse me. Water is protic, so this is. I suppose this must happen in what aprotic electrolyte. I don't know, like an ionic liquid or something. I'm not 100% sure. I'm not really familiar with this exact mechanism. The like oxygen 2-. This particular reaction, the last one on this list. That one I'm not really familiar with, but the most commonly studied and done oxygen evolution OER are the ones in acid and base, and those are those first 2 equations. So, okay, let's see here. Let me go to the next questions and try to wrap this up here. Let's see, Rasmi, we talked about this. We talked about the illumination. Preeti has a question. I did OER using ruthenium. Looks like a spinel, I assume cobalt. I assume you mean not CO304. That's like a spinel cobalt kind of a thing. In 2 different medium, basically acid and base. Okay, the EIS plot I got in acidic medium had 1 semicircle and the basic had 2. What was the possible reason? So acidic had 1 and basic had 2. My guess is that the basic one has to do with the transformation of the cobalt itself. I think it depends on what potential you were doing them at. That for sure. Acidic had 1. Okay, so one of there's my guess is that there's one of two things. The first, and it depends on what potential you did impedance at. Okay, because if you do impedance at open circuit, for instance, you might not even be having any OER. I hope you're doing impedance at a positive enough potential to be studying the OER. So the first possibility is that both did have 2 semicircles or 2 processes, but in acid, the speed and the time constant of those are about the same, and so it looks like 1 semicircle. Semicircles appear as a result of a process, a charge transfer process of some kind, basically, typically, right? And so if the where the semicircle appears is dependent on its speed, its time constant. And so if you have 1 semicircle, it could be 2 or 3 or 4 processes. This is why there's a process called distribution of relaxation times that people sometimes use to try and deconvolute processes of similar time constants. So the first is that might be the case, right? It might be. However, your follow-up question was, can it be due to a cobalt oxidation state change? Yes, it could be. Cobalt, like many transition metal oxides, nickel, iron, cobalt, maybe manganese, have a lot of extra kind of reactivity in alkaline media that they don't have in acid. They form hydroxides, can form oxyhydroxides. So this is like, oh, you could have a cobalt, I guess it'd be like COOH2 or OH3. I don't know exactly what the right oxidation state might be for that situation, but right, you could have an oxidation change in the cobalt, forming cobalt oxide or cobalt oxyhydroxide, which is like OOH. So you could have like COOH, um, CO304 is let's see here. So yeah, check the oxidation state. What's the oxidation state of your cobalt? I'm trying to see. I don't know if you have some sort of combined process, ruthenium combined electrode here. In any case, exactly what your oxidation state is, it could be something related to that. And so yeah, so in alkaline media, it might be something. Now, what you could try doing is changing the potential at which you're taking impedance in both acid and base, and seeing if you see one of these semicircles appear or disappear as you change the potential, and that would be an indication of a process in one of those, particularly alkaline. Decrease the potential and see if one or both of the semicircles go away. If you know, for example, which semicircle is related to the OER, as you decrease the potential, that one should go away because you're not at a high enough potential to do OER. But also you might make the other one go away because you're not at a high enough potential to oxidize, change the state of your cobalt itself. But that is my best guess as well, which is what you also followed up and asked. I do think it's very possible, especially in base, that you're forming some other cobalt species. That's pretty common on transition metal oxides for sure. Let's see. Okay, so yeah, so finally, I know Pranith, you were asking more about the illumination. I'm not sure how to do it. I haven't gone through an entire manual of potentiostat suggestions. Yeah, Chris had some good suggestions. I think run dark, then illuminated, and then dark. There might be a time constant involved that should be determined. Yeah, the in general the procedure is get an open circuit potential, do a quick, again, whatever, I don't know exactly what you're studying. There should be, hopefully you have some literature, I don't know, reference point for yourself, doing like an LSV sweep or doing impedance or some diagnostic test in addition to just checking the open circuit potential. Do that when it's completely dark, covered, and then do it under illumination and compare the two. Getting time constants is a little bit easier out of something like impedance. So that might help you kind of interrogate that those kinds of systems there. But yeah, I mean, honestly, to a certain extent, the suggestion is just start doing stuff. Like you're gonna really quickly start learning and figuring out the ins and outs of your system if you just start running tests, even kind of incautiously, because you're just going to learn as you start probing and changing and turn the lights on and off. See what happens. I do encourage you in that way. Let's see. I think we've reached the end here. I hope I got to everybody's question. I think I did. Again, without Alex here, it's hard to keep track of everything. He's very good with doing this. I like doing it together. So by myself, I hope I've captured all of your questions. If I haven't, my apologies. And please feel free to reach out or leave a comment on this video after it's over, which is very soon, I suppose. But in any case, Chris, good to see you, and you're sort of my remote co-pilot today. I appreciate your help as always. And yeah, everybody else, thank you for joining me today. Yeah, I hope everybody has a great weekend, and we'll see you next time on Ask Us Anything About Electrochemistry. Take care, everybody.